some exercises. So present the exercises. So let's say you have exercises. Okay, number 1. It says that if you have a permutation alpha in the array shape, which has 1, 2, 2, 1, 3, 3, 4, 5, 5 goes to 4, 6 is fixed, and you have another permutation actually we have a permutation which goes 1 to 2, 2 to 1, 3 to 3, 4 to 5, and 5 to 4, and 6 to 6, which is similar. And there is permutation beta, which is 1 goes to 6, 3, 2 goes to 1, 3 goes to 2, 4 is fixed, 5 goes to 3, and 6 goes to 5. Right? What we need to find is alpha inverse. Find alpha inverse and product of beta alpha and the product of alpha beta. Okay. Solution will be, okay, so what do you need to find? When you need to find alpha inverse, then you actually try to invert the alpha, and we have to use the same notation. So the alpha inverse is going to be equal to something which is 1 goes to 2, 2 goes to 1, 3 is fixed, 4 goes to 5, 5 goes to 4, and 6 is fixed. Now there is a reason behind it, because it is same as alpha. Because if you write alpha in the cycle notation, that is 1, 2, 3, 4, 5, and 6. And you can see, if you remove all these fixed ones, you will have 1, 2, and 4, 5. Now this is a permutation which is a product of 2 cycles, and every 2 cycle is its own inverse. Very nice. So you don't need to do anything else. So alpha is its own inverse. Perfect. Now beta. Now for the beta, if you see, it's not a 2 cycle. So the inverse for beta, we don't actually need to find the inverse, but we actually need to find the product of beta alpha. Okay. And the product of beta alpha we can find is by writing beta first. 6, 1 goes to 6, 2 goes to 1, 3 goes to 2, 4 is fixed, 5 goes to 3, 6 goes to 5. And then we write alpha, which is 1 goes to 2, 2 goes to 1, 3 is fixed, 4 is going to 5, 5 goes to 4, 6 is fixed. Now we know a way that what we do, we first look at in the alpha, and then we look at the image of the so if 1 goes to 2, then we will look 2 in beta, and then we send it. Okay, so that means if we write beta alpha, then if 1 goes to 2, but in beta, 2 goes to 1, so 1 goes to 1. Now 2. In alpha, 2 goes to 1 and then 1 goes to 6, so 2 goes to 6. Similarly, 3 goes to 2. Similarly, 4 goes to 3, 5 goes to 4, and 6 goes to 5. That is going to be beta alpha. And we can write alpha beta using the same procedure, but I'm going to write the answer only. That is going to be 1 goes to 6, 2 is going to be fixed, 3 is going to be 1, 4 is going to 5, 5 is going to 3, and 6 is going to 4. Alpha beta is not equal to beta alpha because the symmetric group is not symmetric, is not commutative, is not abelian. Okay, perfect. Number 2. Number 2 says if we have a permutation alpha, which is 1 goes to 2, 2 goes to 3, and 3 goes to 4, 4 goes to 5, 5 goes to 1, 6 goes to 7, 7 goes to 8, and 6 goes to, 8 goes to 7. Sorry, it should be 6. Perfect. We have a permutation beta, which is 1 is fixed, 2 goes to 3, 3 goes to 8, 4 goes to 7, 5 goes to 6, 6 goes to 5, 7 goes to 2, and 8 goes to 4. A. You need to write. Question is write alpha, beta, and alpha beta is. A is products of the joint cycles. B is product of two cycles. Perfect. Solution. So first, let's write alpha is the product of disjoint cycles. A. So alpha is going to be that 1 is going to 2 and 2 is going to 3. So I can write 1, 2, 3, and then 3 is going to 4. So I can write 4. And then 4 is going to 5. So I can write 5. And then 5 is going to 1. So I can close this cycle. Perfect. Then I can write 6, which is going to 7. Then 7 is going to 8, and 8 is going to 6. So that's a complete cycle. Close it. Then we can write beta, which has 1 fixed. Okay, there's 1 fixed. So we don't write 1. We start with 2, which is going to 3. And then 3 is going to 8. And then 8 is going to 4. And then 4 is going to 7. And then 7 is going to 2. So it's a complete cycle. The remaining thing is 5 goes to 6 and 6 goes to 5. Perfect. Now that is A. Now B is going to be that alpha is 1, 2, 3, 4, 5, and 6, 7, 8. Now I need to write this as a product of two cycles. So, okay, and then there is alpha beta. So first you need to compute alpha beta, and then you need to write it. So I can write the part remaining in alpha A is alpha beta. So alpha beta is, if you compute it, that's going to be 1, 2, 4, 8, 5, 7, 3, 6. You can check the product of alpha beta in cycle notation is going to be this one. Now let's come back to part B, where we need to write alpha is a product of two cycles. So you can write alpha is a product of two cycles by writing 1, 5, 1, 4, 1, 3, and 1, 2. And then you can start 6, 8, and then 6, 7. That's our alpha. Now beta is the permutation which is 2, 3, 8, 4, 7, and 5, 6. We just need to write 2, 7, 2, 4, 2, 8, and 2, 3, and 5, 6. That is our beta in two cycle notation. And then remaining one is alpha beta, which is the permutation 1, 2, 4, 8, 5, 7, 3, 6. I can start it writing by 1, 6, 1, 3, 1, 7, 1, 5, 1, 8, and 1, 4, 1, 2. And that's it. That is number 2. Okay, perfect. Now, let's find the order of the permutations. So number 3 is find the order of each permutations. Okay, so A is 1, 2, 4, 3, 5, 7. Its order is I'm writing the solutions according. Okay, let me write the question first. B is 1, 2, 4, 3, 5, 6, 7. C is 1, 2, 4, 3, 5, and D is 1, 2, 3, 5, 2, 4, 5, 6, 7. Wait. Yeah. Okay. Now a solution. A. We know that the order of a permutation is the LCM of its cycle type. That is going to be 3, 3, which is 3. B. LCM of 3 and 4, that is going to be 12. C. LCM of 3 and 2, which is going to be 6. And D, which is going to be LCM of 4 and 5. Right? But the permutation, so D is quite tricky. So in the permutation D, if you need to find the order of this 1, 2, 3, 5, and 2, 4, 5, 6, 7. Remember, you need to find the order of the LCM of disjoint cycles. this permutation have common elements. So first you need to write is the order of disjoint cycles. That is going to be that you write is 1 2 4 and then 3 5 6 7, right? And then you can write the LCM of 3 and 4, which is going to be 12. Perfect. That's how you find the order of the permutations. Now, what are the possible orders for elements of S6? That kind of question we have done previously. So, what are the possible orders for elements of S6 and A6? And then what about A7? Okay, solution. So we write a cycle and then we write its order along with it. What is the procedure? We find the orders by looking at the possible products of disjoint cycle structures arranged by longest length left to right and denote by n cycle. Okay, so this one, it has order what? Is order 6 and then 5 1, and then we have it has order. So let me write in this way so you can identify this is the order, and then order of 4 2. This is LCM of 4 and 2, which is going to be 4. And then I can write 4 1 1. That is LCM of 4 1 1, which is going to be 4. Then I can write 3 2 1. And if you follow the same procedure, you have 3 2 1 that has LCM 6. And then I can write 3 1 1 1, and this has order 3. And then I can write 2 2 2, which is order 2. Similarly, I can write 2 2 1 1, which is also order 2. Similarly, I can also write 2 1 1 1 1, which is order 2. And then finally, the last one have order 1, which is going to be an identity. So for say S6, the possible orders. So for S6, the possible orders are going to be 1 2 3 4 5 6. Okay. Now For A6, the possible orders are 1, 2, 3, 4, and 5. Why? Because in A6, the cycle type is going to be similar to the cycle type in S6, S6, symmetric group on 6 elements. Okay, perfect. Now we see from the cycle structure S7 from the cycle structure of S7 in example 4 that in S7 the possible orders are 1, 2, 3, 4, 5, 6, 7. Perfect. Now let me choose few exercises which are useful. So there is this exercise which says that number 5 now says that show that a function from a finite set S to itself is 1 to 1 if and only if it is onto. And then is this true when S is infinite? Perfect. So let's say S is a set which has elements S1 to Sn, right? And phi is 1, 1, 1 to 1 from S to S. Phi is the function from S to S is 1 to 1. Okay? Then phi of S1 to phi of Sn are all distant and all in S. So phi of S is S. On the other hand, if phi of Si is phi of Sj for some I not j, then phi of S has at most n minus 1 members, right? And the mapping from Z to Z, and that makes that first thing true. Now the last one, which says that is this true when S is infinite? So let's say S is late, S is Z, then psi is a function from Z to Z that takes x to 2x is 1 to 1 but not onto. Okay, so in the infinite case it is not possible. Perfect. Right. Now the question is number 6 says that late beta is an element in S7, and suppose that beta power 4 is equal to 2, 1, 4, 3, 5, 6, 7. First thing we need to find is beta itself. Then what are the possibilities for beta? Possibilities for beta if beta is in S6. Sorry, S9. Okay, perfect. Solution. So we know that since beta power 24, or not 24 but 28, is equal to beta power 4 power 7, so it is going to be identity permutation. Okay, and we know that order of beta divides 28, but beta power 4 is not itself identity. So order of beta cannot be 1, 2, or 4. That's true. Okay. Now, if order of beta is equal to 14, then beta can be written in disjoint cycles form disjoint cycle form which contains which has 1 7 cycle and 1 2 cycle. But that requires at least 9 samples. But that requires at least 9 samples, and we have only 7. Likewise, if order of beta is 28, requires then it requires 1 7 cycle and 1 4 cycle. So the only possibility is order of beta is 7. Thus beta is equal to beta power 8, which is equal to beta power 4 power 2, which is equal to 2, 4, 5, 7, 1, 3, 6. Okay, perfect. Now in S9, beta is actually equal to 2, 4, 5, 7, 1, 3, 6, or it can be the product of 7 and 2 cycles. That is 2, 4, 5, 7, 1, 3, 6, and 8, 9. Interesting, right? Perfect. Nice. Now, the last one should be, this was 6, one more, 7 is, let's say, alpha is a permutation which has 1, 3, 5, 7, 9. And then we have 2, 4, 6. and we have 8, 10. Now, if alpha power m is a 5 cycle, what can you say about m? Okay. So if you want to say something about m, now since alpha power m is going to be it's going to be the power on each cycle, right? And the result is a 5 cycle. We reduce that. The result is a 5 cycle. So so that means 2, 4, 6 power m is identity, and 8, 10 power m is also an identity. So 3 and 2 divides m. Now since 1, 3, 5, 7, 9 power m is not an identity, we know that 5 does not divide m. 5 does not divide m. Thus we can say that thus we can say that m is a multiple of 6, but not a multiple of 5 or 30, but not a multiple of 5 or 30. Perfect. Here we will end our this part of the lecture. Thank you so much.